All right. So what'd you think? Pretty fun. Fun idea. So what we're going to do now is, oh, Nadia didn't like it. So what we're going to do now is just quickly break into breakout rooms and discuss the questions that I have posted on that tasks list. Specifically, how did they experience zero gravity in a plane? What was the plane doing? Were they experiencing zero gravity for the whole plane ride? Did you notice any moments where gravity seemed to return in the music video? Do their motions look normal or sped up slightly? So just chat about those. I'll break us into a couple breakout rooms now, and we'll do this for about 4 minutes, and then we'll come back together. So I'm just going to randomly assign everybody to rooms. Let's do about, let's say 4 rooms. All right, go for it. All right, so it looks like some of you did get at it. How did they create this seemingly zero gravity? What was the plane doing? Yeah, seems like I see some of you doing this, right? So a lot of you got that the plane was in free fall, but a lot of you pointed out, or hopefully you noticed, that the video is 3 minutes long. If a plane goes into a dive and dives for 3 minutes, what's going to happen?
Crash.
Yeah, it'll hit the ground, right? You can't free fall that long. A lot of skydivers and stuff, people who even parachute, you really don't get, I mean, you get like less than a minute of actual free fall before you need to, deploy your parachute because you're going to hit the ground way too fast. That Felix Baumgartner video that we watched before, that was the longest free fall anyone's ever experienced because he was so high up, higher than most people have gone to actually jump out. Airplanes can obviously go high, but they were flying in parabolas, so they would drop and then rise up again and drop. So did you guys notice in the music video a couple times they all kind of got back in their seats, or they would,
at the very end?
Yeah, you would notice like the balls floating around would suddenly drop, and so gravity did return for a bit, but then they went back into free fall. And you'll see there's a little bit of editing that they did to fix that. So all right, I would now like you to complete a quick ed puzzle that I created. Based on another video. It's about 5 minutes long, which is about how this video was made. And it's kind of interesting to see both how they did it and also what the experience was like for them trying to figure out how to dance and do this. So go ahead and work on that. It's, again, a little more than 5 minutes long. I'm going to time us for about 8 minutes, and then we'll come back together again. And again, this is task number 2 right there on the ed puzzle. So 9 minutes, go for it. And again, I'm listening here if you have any questions or something isn't working. So go for it.
Mm-hmm. I don't know.
Well, so I mean, this is just, it's an overly specific question, but what was there was something that they talked about that they noticed about filming in zero gravity when they tried to move in zero gravity. What does it look like?
They're in slow motion.
Yeah, it looked like they were in slow motion. And so this was sort of an added benefit that by they had to stretch the song out just to make the best use of the time that they were in zero gravity, but it also meant that they were able to speed it up just a little slightly, so their motions look a little more natural. They don't if you watch the video again, you'll notice that things are actually sped up a little bit. So it gets rid of that slow motion effect. Yeah, that's what I was getting at with that question.
All right.
Kind of a silly question, but yeah. All right, yeah, let's come back together. It looks like most of you who were able to get the ed puzzle working have gotten it done. For those of you who didn't, I apologize for it not working. I had a couple students have issues with this too in the previous lesson. So anyway, I'll try to look into what's going on. It's weird that it works for some but not others. That's what's weird about it. I feel like if it didn't work for everybody, I could figure it out. But anyway, but if you were not able to look at the questions, let's take a look together really quickly. And I also just think this is kind of fun and interesting. Ambitious project that they took on. So first of all, for the multiple choice, in terms of understanding what's happening here, a lot of you are exactly right. The airplane's flying in parabolas, but the reason that this works and what's happening with this is they experience double gravity on the rise, zero gravity as they come over the arc, and then double gravity again as they kind of come out of that. And the best way that I can think about it is throwing something in the air. So if you've got something around you like a pen or piece of paper, something that you can just grab and toss up and down real quick. Grab that object, just give it a little toss up in the air. Doesn't have to be very high. But I know it's weird to think, but when they were flying in those parabolas, this is what the airplane was doing to them. So the airplane was essentially throwing them into the air. And so that was that initial, when you throw your pen or whatever it is, you are exerting about double gravity, 2Gs, onto that pen, right? Because it's experiencing 1G on its own. And when you throw it upwards against gravity, you're giving it another, at least another G's worth of force. Then as it rises up and comes to a stop, that's that sort of zero gravity moment, right? It's in free fall. And then when you catch it again and it comes to a stop very briefly, it experiences again those double G forces because gravity returns and you're also taking control of it again, catching it. And so that's what the airplane was doing to them essentially, which is weird to think. But I think it also emphasizes a good point that were they actually experiencing zero gravity? I know that's the term they use in the video, but were they experiencing zero gravity?
No.
They weren't. They were experiencing just as much gravity as any of us are, right? What was happening was that they were falling inside of an airplane, and they're falling with the airplane. So, and this is a term we used before, but they had no apparent weight, right? Meaning that they seemed to be weightless, even though in reality they all were experiencing gravity, they're just falling. But if you had a bathroom scale inside that airplane in that free fall moment when they're all floating around, if they tried to stand on a bathroom scale, would it register any weight for them? It wouldn't, right? Because again, everything's falling together. So that's why we say they have no apparent weight, even though they were still experiencing as much gravity as we are here on the ground as well. So even though they cut out those waiting periods, and we talked about this earlier, there are moments in the video when they get back in their seats, when you see all the knickknacks that are loose fall back down to the ground, and then suddenly everything floats back up again. So there are those moments when you could see where the diving was happening. And they make a point in the video that was gravity like a switch? Did they go from being, to having weight to being totally weightless, or was it more gradual? Anyone remember from the video? Was it quick or was it gradual?
Gradual.
Yeah, it was more gradual, and that made the filming even trickier, right? Because they had to figure out the exact moment when, okay, go for it. You can try to dive out of your seat. Anyway, it must have been kind of a weird feeling. So, all right, what are the two common ways that people respond to weightlessness?
Swimming and puking.
Yeah, just kind of funny. Like I feel like I would probably do both, but it's funny to think that we just try to swim, and we'll get at what's going on with the puking. And yeah, the last question, again, it just made their motions look more natural, because when you're in slow motion, when you're in zero gravity, it looks like slow motion. But by stretching out the song, and it looked a little more natural, I think, their movements. Even though if you watch it, you can kind of see that it's sped up. So, all right, but I want to now focus on that second to last question about the nausea. And let me pitch this to you. So how do we experience gravity? Think about your body and your biology. How do you know which way is down? Does anyone know what sense organ figures out that you are, when you're lying down, that you're on your back, or if you're hanging upside down? How do we feel that?
Your ears.
Stomach definitely plays a role, but yes, it is. The main mechanism is actually inside your ears. It's weird to think, but in the internal structure of your ears, you have these sort of looped canals that are full of liquid, and that liquid moves with gravity, right? When you're standing up, it's in a certain position. When you lie down, it moves, and there's all these little tiny hairs essentially in the liquid that move around as the liquid moves, and that's how our body very quickly determines if our orientation is changed. And it's kind of cool that we have based technology on this. Your smartphones, a lot of you have iPhones. Have you guys noticed that if you are holding your iPhone and you suddenly turn it sideways, have you guys noticed that the screen also corrects itself? They have put essentially an ear mechanism in the iPhones. It's based off our own biology. There's a little tiny mechanism in there. I don't think it actually has liquid in it. I think it's more metal, sort of a magnet. But the point is that it rolls around with gravity, and the screen is able to then figure out which way is up, which way is down. But you're right, there are other organs, right? You can sense where your blood is, right? When you're hanging upside down, your head really fills up with blood. You can feel that. Your stomach definitely starts to feel a little weird. And I think it's your vision as well, your eyesight. We know based on just the horizon and our body position what things look like. And it gets kind of interesting. How do you think you feel when what you're seeing doesn't match up with what your ears are sensing in terms of your body position or movement? Does anyone know how that makes you feel if things don't line up?
Nauseous?
Yeah, right. You feel sick. Think about being on a boat, right? A lot of people on a boat have problems because they're either looking at the boat or they're looking at the horizon, which appear to be stable, right? But your ears are telling you, no, we're moving around right now. We're sloshing back and forth, and you feel really, really bad. Anyone ever experienced car sickness before? So that's kind of a very similar thing where, especially if you try to read in a car, some people can do it, but some people get really sensitive, right? If you're reading in a car, because you're looking at something that is still, but your ears are like, wait, we're moving forward. We're sensing this movement. And so the same thing is happening when you're in the zero gravity, right? I think a lot of people get really sick on that airplane because you're in an airplane room that looks like it's not doing anything, and yet you're feeling all this motion and force. You're going from being weightless to having weight, and so that can really add to the nausea. So you can see they were on like really intense anti-nausea medications to film the whole thing. So, but I want to kind of play around with that today. We're going to explore in the next part of chapter 5 is all about the biology of ears and how we sense gravity and your sense of balance. But I want to do a quick activity away from your computers, kind of silly, but it's just to play around again with your sense of balance. I'm going to show you a demonstration video. This one I will actually play through Zoom. Pull it up here. Hi, Science 2 kiddos. I'm going to do a couple of balancing activities today. The organ that gives you a sense of balance is everyone hearing me and seeing me? Cool. All right. Actually, your ears, and we're going to learn some of the details about that, but that is how we perceive gravity and get an idea of which way is down, which is something we've been working on. But your vision and eyesight also plays an important role, as you'll see. So to play around with your sense of balance, we're going to be using our feet, standing on one leg and using your feet to move objects from one container into another. So you'll need something that you can either pick up with your toes by grabbing it, or that you can scoop your foot under it and lift and move. You could use bean bags if you have bean bags at home. I kind of made my own bean bags, just took Ziploc bags. This one's full of Cheerios, so you can use cereals if you want. But don't be wasteful. Like, I'll put these back in so that we can eat them. If you've got like some kind of little toy that's in multiple pieces, these are like little magnetic letters from the fridge. You could even like use candy. This is a bag full of Butterfingers. Hopefully I won't be a Butterfinger and drop it. Get it? Or if you're really up for a challenge, you could use something heavier, like this is a bag of cuties, or maybe even like a bag of potatoes or something. That would be a pretty big challenge for balance. However, you only need 3 of them, right? So I'll get rid of it. All right, and so what you're going to do is transfer these 3 items from one container into another. So you need something, you can see I have a basket and just a pot here at home, but whatever large container you have, just get 2 of them. Make sure the bags can fit inside of them. You want to make sure you're in an open space and somewhere safe where you're not going to fall and like hit your head on anything dangerous, and you want to be able to like spread your arms out, because that's going to be an important part of balancing. We're going to do this in 4 different ways, and always use the leg that corresponds with the motion. So if you're moving the items from the right to the left, use your right leg, right to left, right to left. If you're moving the items from left to right, use your left leg, go this way. You'll see that by crossing over, it actually makes the balancing a little harder. You're welcome to try that if you want, but I'll just keep these simple. So the first round, you just want to have your eyes open and your arms out for balance. And again, just transfer the 3 items, like so. These are a little more challenging for me. All right. The next round is the same thing. You can have your arms out, but now you've got to have your eyes closed. So, and notice again, I'm using my other foot now because I'm going from left to right. So just get an idea of where your containers are, but then close your eyes and see if you can bring the items over. See, it's a little more challenging. Oops. Okay. All right, 3rd round, you want to have your eyes open again, but this time your arms are held behind your back. Again, I'm using my right foot to go from right to left. Cuties are definitely hard. Okay, for the final round, you want to combine both things. You want to have your arms behind your back and your eyes closed. This should be the most challenging one. So again, get your bearings. Here we go. Again, you'll see that having your vision These seem a little harder. Okay. All right. So your challenge is to do those 4 activities as quickly as you can and film it and upload it with Flipgrid. So you might want to get a parent or guardian or sibling to either help film you or position your camera in such a way that you can film your feet and the ground and what you're doing with your feet. And you can just use the video as your timer, right? So start the video, get set, and then we'll just see who can do it, those 4 activities in the fastest amount of time with the fewest stumbles. So you don't want to rush because if you're stumbling around everywhere, then that's not technically going to count, right? We want to see who can be the most stable and do it the fastest. So that's your challenge. As always, be safe, right? Make sure there's nothing dangerous around you that you're going to fall on. And always clean up after yourself, so make sure you put your items away and emptied your bags once you're done. All right, so that is your challenge. Here is the Flipgrid assignment post. And again, I've summarized it here as well. So again, you're just moving from one container to another. You don't have to go back and forth. You're just going from one container to another. First round, eyes open, arms out. Second round, eyes closed with your arms out. Third round, eyes open, but arms held behind you. And the fourth round, eyes closed, arms held behind you. So those are your 4 things. I want to emphasize safety, okay? Glass doors, swimming pools, staircases, please stay away from those things, okay? I don't want you to end up on America's Funniest Home Videos or something like that, or hurting yourself. So I'll give you about 15 minutes to work on this, maybe a little bit more. But go ahead. I've seen videos of students in the past. They used dog toys. They used whatever you can find. It doesn't have to be specific as long as it's something you can pick up with your foot and move. I'll be here listening if you still need help with anything. But otherwise, just make sure you're posting to the Flipgrid, and you should be able to get it done in 15 minutes. If you can't, it'll just carry over into homework. But I encourage you to try it now. And so we'll come back together in the room here at 11:30. So it's about 17 minutes from now. So plan to be back in here at 11:30. Got it? All right, I'll be here if you have questions. Go for it. I encourage you to go check out each other's Flipgrid videos. There's some pretty entertaining ones out there. We'll see who the winner is with the shortest time and the least little fumbles. So Carmen, I was very impressed, has a very good sense of balance. So anyway, I'll check out. I was able to check out some. Hank chose to use a hat for one of his objects, which proved to be challenging. What kind of hat was it again? It was a bucket hat, I think, right?
Yeah, it was a bucket hat.
Nice. Yeah. Mm-hmm. Anyway, all right. So what did you guys notice? Was it a little bit harder? Like what happened when you closed your eyes?
I don't think my balance was off more so than like just trying to find the objects, and then that made me lose my balance.
Yep.
But it definitely adds.
How about when you had your hands behind your back?
I mean, when I have my vision and like obviously my ears, then it didn't really matter to me, I guess.
Yeah. Yeah, I noticed usually when you take your arms out of the equation, there's a lot more stumbling, right? Because your body's still trying to establish a center of weight. And the reason this is challenging is because by having to move something with your feet, you are changing your body position. Your center of mass is constantly moving. And so that kind of forces your brain to do a little bit more work. And then when you can't use your arms to balance, that's when a lot of you are adjusting your heels and your toes. But it's pretty amazing how sensitive we are to making sure that we stay standing up. And a lot of you might have noticed too, if you've done dynamic stretches before for sports, that if you've done yoga or anything like that too, once you start doing a lot of that and you're bending over, your sense of balance is a little, you're like, whoa, like you've got to put a little effort into it. So, all right, well, you'll be reading tonight for homework about the inner ear and how that works and gives you your sense of balance. So this was just meant to be a silly activity for that. I'll check out the videos. If you didn't get a video posted, you can finish that for homework. The last thing I want to do today, I know we only have like 7 minutes left, but I want to get started on a little instructional video relating to the gravity force PhET simulation that you should have done homework for homework last time. And just to kind of reemphasize the important takeaways from this, I'm hoping it's sort of obvious at this point, it relates to the math, but what do you notice when you move the objects further apart? What happens to the force, the attractive force between them. The greater the distance, what happens to the force?
The weaker the force.
Yep, the weaker the force. So does anyone know, is that directly proportional or inversely proportional? If I increase distance, I decrease force. Is that direct or indirect? Or I should say inversely.
Force and distance?
Yeah,
Yeah, inverse.
yes, should be inversely proportional, right? Whereas you'll notice when we increase the mass, what happens to the gravitational force between them?
Goes up as well.
Goes up. So that's directly proportional. So I'm going to start a very short video that I made. The video is longer than what we'll be able to watch right now, but we'll at least get going on it, about the math and actually exploring some of the math. And I'll offer you a little bit of extra credit if anyone feels up to attempting to solve one of these math problems. So we'll start playing it, and I'll just keep going until the end of the period and then let you guys go. So check out the following. And feel free, if you want to take some brief notes on this, you can, or you can always rewatch it later as well. Hi, Science 2 kiddos. This is my first time using Notability. I know that you've probably maybe seen this in your math classes, but I'm going to use this program to take us through some of the math in physics, specifically calculating gravitational force and calculating what's called the gravitational constant, capital G. So we'll start off by first defining the universal constant of gravity, represented by capital G. We'll then use that same gravity force lab PhET simulation that you worked on for homework to actually calculate the value of G. And then knowing G, we'll use that to calculate gravitational force F. And there's a lot of fancy math here, including scientific notation and canceling units. But if you feel up to it after watching this lesson, for extra credit, this is optional. You don't have to do it. But if you're up for it, for extra credit, you can try one of these calculations on your own at the very end. So this relates to chapter 5.5 from Hewitt. They define the universal constant of gravitation as a very, very small number that represents the weak force of gravity. It sort of puts gravity in context. And it also brings in newtons as a measurement, right? So it's looking at gravity as a force and relating it to, again, mass and distance. So we're adding it into that equation that we looked at before from Newton. It is based on the gravitational force between two 1 kilogram masses that are 1 meter apart. So if you think about it, if you had one mass that was 1 kilogram, and another mass that was 1 kilogram, and they were exactly 1 meter apart, then the gravitational force that each would be exerting on the other would be equal to that very tiny number right there. That is, in newtons, the force. And so we can rewrite that in scientific notation. That's the value of capital G as 6.67 times 10 to the negative 11. Again, that negative exponent there tells you that it's a very, very small number. And it's got a crazy unit on it. It's newtons meters squared per kilogram squared. But that is derived from this equation here, which you're hopefully familiar with, right? This is one we learned about earlier, where F is the gravitational force, and it's showing that it is directly proportional to mass, right? So the larger the mass, the more gravitational force it can exert. And it's inversely proportional to distance. So the further apart two objects are, the less gravity they will exert on each other. G is the constant that's brought in here to sort of bring the Newton's unit in, and also again to put it in context, right? That gravity is a very weak force between these. So let's do some math using this equation. I want to first use our PhET simulation to actually calculate the value of G. If I do this right, I should get that same 6.67 times 10 to the negative 11 up here, right? That's my goal right there. That's what I want to get. So I know my equation right here. Okay, so just to see if you guys can walk me through this. If I was going to use that equation up there, F equals G M1 M2 over D2. Can anyone tell me, I know G, or G is what I'm trying to find. What would the F value be? What number, what do you think F stands for?
Force.
Yeah, it's the force. So it would be that, 33.4 newtons, right? But you'll notice there's two forces, right? We have force from mass 1 and force from mass 2, but what do you notice about that number?
The same.
The same. So that's your F value. Good. What would my M1 be?
2 billion kilograms.
Yep, 2 billion kilograms, right? What about M2?
4 billion.
4 billion kilograms, right? And so I got to write those in scientific notation, which I'll describe in the video. And then what would D be?
4.
Yeah, but one of the issues with this is that the gravitational force constant, that value of G, is actually measured in meters. If you look at the unit, it's meters squared. So we'd have to convert 4 kilometers into meters. Anyone know how many meters in 4 kilometers?
4,000.
4,000. So then it's 4,000 meters. So again, you can keep watching the video on your own. I'll walk you through the math and how to do it. Basically, I solve for G to check that, and then I do another example where I'm calculating F and double check that, and then that's the extra credit. So it's optional, but it's I'll offer you I think 5 extra credit points on homework. It's on the very last slide. So the slides are accessible on that tasks list. Here's the very last one. So here's the example I want you to do. You see I've covered up the force value with these little
It's the very last one.
share the screen. Yeah, it's the very last slide. So here it is. I've covered the force with the little blue boxes. Now obviously you could go to the simulation and like make these settings and it would give you that number, so you can check your answer. But I want you to show the math. So if you do it in your notebook, send me a picture of the math, show me all the work that you did. If you do it online through some other mechanism, just make sure I can see all the math and work that you did to solve this problem. So, again, it's optional, it's not required. This is something more I think our honors kids are doing. The actual homework that I want you guys to focus on, this is what is required of you, is on the very bottom of that tasks list. I would like you to read Hewitt chapter 5.5 through 5.6. It's the next 2 sections. Take notes for a reading quiz, and I would also like you to answer reading check questions 8, 10, 12, and 14. So we're doing the evens this time. 8, 10, 12, and 14. That's on page 116. It's the very end of chapter 5. Do that in your science notebook, post that online. All these assignments should be on Canvas. And make sure you've posted your Flipgrid video. Those are the 2 required things. Otherwise, it's optional to do the extra credit. And also, if you like that OK Go video, this is a longer video. It's about 20 minutes long. That goes into a lot of detail about how they made it and what it was like and how many takes they had to do and how many people were involved. And it's pretty cool if you want to check that out. So, all right. Any questions about any of that? All right. That's all for me today, kids. Thank you very much. Have a good day.
Thank you.
Thank you.